In question 1, we're given that a, b, c are integers greater than 0 such that c is b plus 2 and a plus b plus c is 10. And we need to prove by exhaustion that the product of a, b, and c is always even. So we are provided with a table below that will help us illustrate our answer. So we start by considering different values of a and the corresponding values of b and c, and what kind of product we get for a, b, c. So when b is 1, then obviously c, which is b plus 2, must be 3. And then based on the fact that a plus b plus c is 10, we can see that a is 6, and the product of 6, 1, and 3 is 18, which is even. If b is 2, then c is 4, and a is 4. So again, 4 times 2 times 4 is 32, which is again even. And we can proceed with b being 3. Now if b is 3, then c is 5, and a is 2. So 2 times 3 times 5 is 30, which is even. And I can further proceed with b being 4. Well, if b is 4, then c is 6, and a is 0, which is not allowed because we were told at the beginning that a, b, c are integers greater than 0. Please note that you need to cross out this line in your answer to claim all the marks, and all we're missing is a conclusion to sum up everything we have found here. So to write the conclusion, it's simply copy-paste whatever the question was telling us to do. So we conclude that the product of a, b, c is always even as required. In question 2, we've got the curve f of x, where f of x is 2 minus kx to the 5, k is a constant, and we are told that when f of x is divided by 4x minus 5, the remainder is 243 over 32. We need to show that k is 2 over 5. So we do know that the remainder when f of x is divided by 4x minus 5 is given by f of 5 over 4. Remember, imagine this, setting it equal to 0. So 4x minus 5 is 0, 4x is 5, which means that x is 5 over 4. So this is the value of x we need to substitute in f of x to get the remainder when f of x is divided by 4x minus 5. So let's calculate f of 5 over 4. So this is simply 2 minus 5k over 4 raised to the power of 5. And this must be equal to 243 over 32. Now to remove the power of 5, I will simply say that 2 minus 5k over 4 is equal to the fifth root of 243 over 32. And this is equal to 3 over 2, so 2 minus 5k over 4 is equal to 3 over 2. I could multiply throughout by 4 to get rid of the denominators. So I've got 8 minus 5k is equal to 6, leading to 2 is 5k, and therefore we get that 2 over 5 is k, which is exactly what the question was asking me to do. So as required. Then in part B, we need to find the first three terms in ascending powers of x of the binomial expansion 2 minus 2 over 5x to the power of 5. We need to give each term in its simplest form. So we will be using the binomial theorem here. 2 minus 2 over 5x raised to the power of 5. We start with the full power loaded onto 2, so that's going to be 2 to the 5. Plus 5, choose 1, 2 to the 4 times minus 2 over 5x, plus 5, choose 2, 2 to the 3, minus 2 over 5x all squared, plus dot, dot, dot. Remember that the powers should always be adding up to the original power, which is 5 in this case. So this was 1 and 4, it's also 5. So substituting the values on the calculator, we get a simplified answer of 32 minus 32x plus 64 over 5x squared plus dot, dot, dot. So we were only being asked to find the first three terms of this expansion. And then in part C, we need to use the solution to part B and make our method clear to determine the gradient of C at the point where x is 0. So starting with the result we have established from part B, we had that f of x is equal to 32 minus 32x plus 64 over 5x squared plus dot dot dot. So to find the gradient of the curve at the point where x is 0, I simply need to do differentiation. So f dash of x, the 32 vanishes, the minus 32x will give me minus 32 plus 64 over 5 times 2x plus dot dot dot. Now if I substitute 0 here, so f dash of 0, we simply see that this will give me a result of a negative 32, and the rest of the terms will contribute 0 because they will involve an x term, an x squared term, and so on. So the gradient of the curve C at x is 0 is simply minus 32. In question 3, we've got a sequence defined by an is cos squared of n pi over 3. We need to find the exact values of a1, a2, and a3. So I will simply be substituting n is 1, n is 2, and n is 3 into the given expression to get the first 3 terms. So for a1, we will be doing that this is cos squared of pi over 3, which gives an answer of a quarter. For a2, this will be cos squared of 2 pi over 3, which is also a quarter. And for I, we have that a3 is cos squared of 3 pi over 3, which gives an answer of 1. In B, it says, hence find the exact value of the summation from n is 1 up to 50 of n plus cos squared n pi over 3. So before I actually consider this summation and how to get the result, I will actually move on into calculating a few more terms just to see the pattern of the original sequence, the AN sequence. So I will be finding a4, a5, and a6. So a4 is cos squared of 4 pi over 3, and this gives an answer of a quarter. a5 is cos squared of 5 pi over 3, which also gives an answer of a quarter. And a6 is cos squared 6 pi over 3, which gives an answer of 1. So we see that this sequence goes a quarter, 1, then a quarter, 1, and it keeps repeating. So we conclude that this is periodic with order 3. Now the order means the number of terms to see all the range of values of this sequence. So this sequence repeats every 3 terms, so it's periodic with order 3. Now to evaluate the sum from n equals 1 up to 50 of n plus cos squared n pi over 3, I will start by splitting this summation into the sum from n equals 1 up to 50 of n plus the sum of cos squared n pi over 3, again from n equals 1 up to 50. So if we write out the first few terms of each summation just to see what's happening, we get for the first one 1 plus 2 plus 3 plus dot 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 up to 50. And then for the summation of cos squared n pi over 3, we have already established that it is periodic with order 3. So I'll be seeing a quarter plus 1, and this will be repeated, so dot dot dot, and then a quarter plus 1. And if you think about it, we've got 50 terms summed up here, so we can see that we've got 16 full periods. Each period is 3 terms, and then another 2 terms, which is going to be the next 2 terms of the next period. So it's going to be plus a quarter. So what we are looking at is an arithmetic sum. The first summation is an arithmetic sum. So arithmetic series, it starts at 1, so the first term is 1. The common difference is 1, and we're looking at 50 terms. whereas the second summation here, it's gonna be 50 terms. So we've got 16 repetitions of a quarter plus 1, and then the quarter and the quarter, the last two terms, to make a total of 50 terms. Now, for the arithmetic sum, we know the formula, it's given in the formula booklet. It is n over 2 and 2a plus n minus 1d, and the summation of the cos squared sequence here, it's simply gonna be 16 times, we said, a quarter plus 1 plus a quarter plus a quarter. Put everything on the calculator, you get an answer of 2,599 over 2. In question 4, we've got the weight of a baby mammal monitored over a 16-month period, and the weight, W kilos, is given by this relationship here, where T is the age of the mammal in months and A is a constant. We are additionally told that when T is 3, the weight is 10 kilograms, and we need to show that A is 1.072, correct to 3 dps. So I will start by saying we know that when T is 3, then W is 10, and I will substitute into the given model here. So we've got that 10 is log of 3 plus 5 base A minus log of 4 base A. So we've got that 10 is log 8 base A minus log 4 base A. We know that when we've got subtraction of logs, we do log of the quotient. So 10 is log of 8 over 4 base A, leading to 10 is log 2 base A, and the way to undo the logarithm is to do A to the power of 10 is 2. So A is simply the 10th root of 2, which gives an answer of 1.07177 which of course rounds to 1.072 as required by the question. Now in these questions that say show that, for example, this case alpha is 1.072 correct to 3 dps, you need to show an intermediate working which matches a greater accuracy than the final answer, so that you show the rounding to 1.072 in order to match exactly the answer provided in the question. We are then told to use A is 1.072, so do not use the exact value here. We're going to go with the rounded to 3 dps answer to find an equation for T in terms of W. So I will start by writing out that we've got that W is log of T plus 5 base A minus log of 4 base A. I will not substitute A with the 1.072, I will leave it for the end. So I can combine the two logs together to say W is log of T plus 5 over 4 base A. So that means that A to the W is T plus 5 over 4. Remember, we're trying to get an expression for the model for T in terms of W, so we need to make T the subject of the formula here. So I will cross multiply to get 4A to the W is T plus 5, leading to 4A to the W minus 5 is equal to T, and therefore 4 times 1.072 to the W minus 5 is equal to T. In part C, I need to find the value of T when W is 15, giving my answer to 3 significant figures. So we will start by saying that if W is 15, then we get that 4 times 1.072 raised to the power of 15 minus 5 should be giving me the value of T. So this turns out to be 6.35 months. In question 5, we need to show detailed reasoning and solutions relying entirely on calculator technology are not acceptable. Well, so we need to make sure that we are showing every single step of the work here. And we start off by having to show that the equation 3 cos theta minus tan theta times cos theta is 2 can be written as a quadratic in sign. So let's start with what we are given. The first obvious step is to write tan theta as sine over cos, so 3 cos theta minus sine theta over cos theta times cos theta is 2. I could then expand to get 3 cos squared theta minus sine theta is equal to 2. We do know that cos squared plus sine squared is 1, so I'll be using this identity to substitute cos squared with 1 minus sine squared. So 3 times 1 minus sine squared theta minus sine theta is 2. So 3 minus 3 sine squared theta minus sine theta is 2. And I will collect everything on the right hand side to get 0 is 3 sine squared theta plus sine theta minus 1 as required. In B, it says, hence solve for x between minus pi over 2 and pi over 2, the given trigonometric equation here. We see the relationship with the original, the theta became 2x, so this can simply be written as 3 sine squared 2x plus sine 2x minus 1 is 0, a quadratic in sine 2x. I'll be using the quadratic formula to derive the values for sine 2x. Remember, I cannot just use my calculator to extract the answers. I need to show detailed working. So I need to show the substitution into the quadratic formula. So we get that sine 2x is minus b plus minus b squared minus 4ac square root and all of it over 2a. So this gives values for sine 2x of minus 1 plus root 13 over 6, or sine 2x is minus 1 minus root 13 and all of it over 6. We then proceed into finding the principal values. So for the first one, the PV is shift sine of minus 1 plus root 13 over 6, which gives an answer of 0.4491 ... Whereas for the second one, the principal value will be shift sine of minus 1 minus root 13 over 6, and this gives an answer of minus 0.87507 ... And remember that the principal values will be used to find all solutions within the range of minus pi over 2 to pi over 2 using the appropriate formulae. So for the principal value of 0.44921, we have that 2x is the principal value plus 2 pi k, or that 2x is pi minus the principal value plus 2 pi k. Whereas for the second principal value, we have that 2x is minus 0.87507 ... plus 2 pi k, or that 2x is pi minus negative 0.87507 ... plus 2 pi k. I need to make x the subject and then generate all solutions. So if I take the first one and divide throughout by 2, I get x is 0.22467 ... plus pi k. And if I take the second formula here and divide by 2, I get that x is 1.34618 ... plus pi k. Whereas in this case, I will again divide by 2 to get x is minus 0.43753 ... plus pi k, or x is 2.0083 ... plus pi k. Remember that the x takes values from minus pi over 2 to pi over 2, so the solutions are x is 0.225, 1.346, minus 0.438, or minus 1.133. I'm giving answers to 3DPs. The mark scheme would accept anything correct to 3 significant figures. In question 6, we are provided with a table of values for x and y is f of x, and we need to use a trapezium rule with all the values of y to find an approximation for the integral of f of x from 0 to 2, giving our answer to 3 decimal places. So we know that the integral from 0 to 2 of f of x dx will be approximately a half times the height of the trapezia, which is the difference between two consecutive values of x in my table. So that's going to be 0.5. And then it's going to be the first and the last y value once, and then all intermediate values of y twice. So 2 times 2.6833 plus 2.4 plus 2.1466. Be careful when you plug everything on the calculator. It should give you an answer of 4.84495. Remember, we need to give our answer correct to 3 decimal places. So that's going to be 4.845 to 3 dps. We are then given the region R, which is bounded above by C1, where C1 is the curve with the equation y is f of x, and it is bounded below by the curve C2 with the equation y is 2 minus a quarter x squared. And we are told that this region forms a part of the design of a logo shown in figure 2. So here's the logo here. And we need to use calculus and the answer to part A in order for us to determine the percentage of the logo which is shaded. So essentially we need to find the shaded region here and express this area as a percentage of the total area, which is obviously a rectangle measuring 2 by 3, so the total area is 6. So the focus here is to find an estimate for the region R. We know that since it is bounded above by f of x and below by 2 minus a quarter x squared, then the region R is simply going to be given by the integral from 0 to 2 of f of x minus 2 minus a quarter x squared. Remember, we need somehow to use our answer to part A, so I will start by splitting the integral of this difference into the difference of the integrals. So that's going to be the integral from 0 to 2 of f of x dx minus the integral of 2 minus a quarter x squared dx, again from 0 to 2. Now we've got an estimate for the integral from 0 to 2 of f of x dx from part A. This is 4.845. And then I will do analytic integration for the second integral here. It's giving me 2x minus a quarter times x cubed over 3. Remember, we are increasing the power by 1, dividing by the new power, and I need to substitute the limits. So this is giving me 4.845 minus 2 times 2 minus a quarter times 2 cubed over 3. This is the upper limit substituted, and when I substitute the lower limit, I see that this will give me 0 because both of these will vanish. So plug this on the calculator, get 1.5116 ... This is the shaded region, and I still need to proceed in finding the percentage which is shaded. Remember, the total area was a rectangle measuring 2 by 3. So the percentage which is shaded is going to be 1.5116 ... over 6 times 100, which gives an answer of 25.2%. In question 7, we're given the curve C with this equation, and we need to start off for 3 marks to write the equation in the required form here. So starting with y is 12x cubed times x minus 7 plus 14x times 13x minus 15 over 21 root x. We will start by expanding the numerator to give me 12x to the power of 4 minus 84x cubed plus 182x squared minus 210x over 21 root x, which I will write as 21x to the half. And I will now express this on a term by term basis. So that's going to be 12x to the power of 4 over 21x to the half minus 84x cubed over 21x to the half plus 182x squared over 21x to the half minus 210x over 21x to the half, and I'm looking for simplifications. Now 12 over 21 is 4 over 7, and x to the 4 divided by x to the half. I subtract the powers, so that's going to be x to the 7 over 2 minus 4x to the 5 over 2 plus 26 over 3 x to the 3 over 2 minus 10x to the half, which completes the first part of the question. In B, we are told that the curve C has 3 turning points, and we need to use calculus to show that the x-coordinates of these turning points are given by this cubic equation here. So obviously, I will need to differentiate. We start with the expression we got for y, and we're going to differentiate to get an expression for dy dx. So we get the power down, and we deduct 1 from the power. So 4 over 7 times 7 over 2x to the 5 over 2 minus 4 times 5 over 2 x to the 3 over 2 plus 26 over 3 times 3 over 2 x to the half minus 10 times a half x to the minus a half. I will multiply out this to give me 2x to the 5 over 2 minus 10x to the 3 over 2 plus 13x to the half minus 5x to the minus a half. Now we know that when we refer to turning points, these are points that satisfy that dy dx is equal to 0. So we will set the expression we just obtained to be equal to 0. So 2x to the 5 over 2 minus 10x to the 3 over 2 plus 13x to the half minus 5x to the minus a half is 0. Looking at what we need to arrive at, we can see that the coefficients are right. So 2, negative 10, 13, and negative 5. And we have an issue with the powers. So how can I go from a minus 5x to the minus a half into a negative 5? I will multiply by x to the half. And actually, if we multiply throughout by x to the half, we will recover exactly the printed answer. So I will multiply throughout by x to the half, which leads to 2x cubed minus 10x squared plus 13x minus 5 is 0, which is exactly what we had to show, so as required. In part C, we're given that the x-coordinate of one of the turning points is 1, and we need to find, using algebra, the exact x-coordinates of the other 2 turning points. Well, we know that if x is 1 is a solution, then x minus 1 must be a factor, so that we can proceed with the long division. So we've got 2x cubed minus 10x squared plus 13x minus 5 to be divided by x minus 1. Remember, we're trying to match the highest order term found on the left, so I will multiply by 2x squared, leading to 2x cubed minus 2x squared, and we deduct. This gives me minus 8x squared plus the 13x minus 5. And then I will multiply by negative 8x, so minus 8x squared plus 8x. So again I deduct, and I get 5x minus 5. So this time I multiply by 5, leading to 5x minus 5, and this gives a remainder of 0 as expected, which means that at the moment we've got that 2x cubed minus 10x squared plus 13x minus 5 can be factorized into x minus 1 times 2x squared minus 8x plus 5. Remember, we're trying to solve this being equal to 0, so obviously either x minus 1 is 0 or the 2x squared minus the 8x plus 5 is equal to 0. The x is 1 on the left-hand side is the stationary point that was actually provided by the question itself. Now, for solving 2x squared minus 8x plus 5 is 0, we will be using the quadratic formula, which means that we have that x is minus b, so minus negative 8, plus minus b squared minus 4ac square root, and all of it over the 2a, so the 2 times 2. Plug everything on the calculator to get that x is 4 plus minus root 6 over 2. In question 8, we've got a geometric sequence. First term is a, common ratio is r, and we are told that the sum to infinity is 3a, and we need to show that r is 2 over 3. Well, we know that the sum to infinity for a converging geometric sequence is given by a over 1 minus r, so that means we can substitute sum to infinity with 3a is equal to a over 1 minus r. Well, the a with the a will cancel out, and I will cross multiply to get 3 times 1 minus r is equal to 1. Let me expand to get 3 minus 3r is 1, leading to 2 is 3r, and therefore we obtain that r is 2 over 3 as required. We are then told that u2 minus u4 is 16, where uk is the kth term of this sequence, and we need to find the value of s10, giving our answer to 1 decimal place. Well, let's start by reminding ourselves that the nth term of a geometric sequence with first term a and common ratio r is given by a r to the n minus 1, which means that the second term u2 is simply a r, which is 2a over 3, since we have found r to be 2/3. And similarly, u4 is a r cubed, which is a times 2 over 3 to the power of 3, which gives an answer of 8a over 27. Now we know that u2 minus u4 is 16, which means that 2a over 3 minus 8a over 27 should be giving me an answer of 16, and I will solve this to find the value of a. I will multiply throughout by 27 to get rid of the denominator of 27, leading to 18a minus 8a is equal to 432. So 10a is 432, leading to a being 216 over 5. Remember, we're trying to find the sum of the first 10 terms. We're trying to find S10, and we've got a formula for the sum of the first n terms, which says that this is given by a times 1 minus r to the n over 1 minus r. So in our case, S10 will simply be the a, which is 216 over 5, times 1 minus r, which is 2/3 raised to the power of 10, over 1 minus r, so 1 minus 2/3. Let's plug everything on the calculator. We get 127.3525 ... which to 1 decimal place would be 127.4. In question 9, we've got a curve C1 with equation y is x cubed minus 5x squared plus 3x plus 14. We are told that point T here is a minimum turning point of C1, and we need to use the figure 3 and calculus to find the coordinates of T. So calculus means differentiation in this case. So starting with y is x cubed minus 5x squared plus 3x plus 14, we will proceed in finding an expression for the y dx. Remember, we are getting the power down, deducting 1 from the power, which leads to the y dx being 3x squared minus 10x plus 3. We then know that for a turning point, dy dx should be 0. So dy dx is 0, takes us to 3x squared minus 10x plus 3 is 0. This is a quadratic in x, which factorizes into 3x minus 1 times x minus 3. So we have that 3x minus 1 is 0, or x minus 3 is 0. So we have that 3x is 1, so x is a third, or x is 3. If we go back to the figure here, we see that we've got a turning point here, a maximum turning point, and then a minimum turning point. So it's first the x is a third, and then the x is 3. So we can see that at the point T, x must be 3, and we will use that to find the y coordinate. So at T, x is 3, which means that y can be found by substituting 3 into the expression for the curve. So it's going to be 3 cubed minus 5 times 3 squared plus 3 times 3 plus 14, which gives an answer of 5, and therefore we conclude that t has coordinates 3, 5. We are then told that the curve C1 intersects the circle C2 at the point A with x coordinate 2, and we need to find an equation for the circle C2. Well, let's revisit our figure here. We've got C1 intersecting C2 at the point A. We have already established that the coordinates of t are 3, 5. This is the center of the circle. So we know that at point A here x is 2. So point A is a point on the curve C1. So I will use the equation of the curve C1 to find the full coordinates of point A, and then use the distance formula to find the distance between A and T, and that will give me the radius of the circle. So we know that at A, x is 2, which means that y can be found by doing 2 cubed minus 5 times 2 squared plus 3 times 2 plus 14, which gives an answer of 8, and therefore A has coordinates 2, 8. The radius is simply the distance between the center of the circle and a point on the circumference, so it's AT in this case. So we're doing y2 minus y1 squared plus x2 minus x1 squared and all square root to find the distance between A and T, the radius. This turns out to be root 10. And we know that a circle centered at the point alpha beta having radius r has equation x minus alpha squared plus y minus beta squared is r squared. Well, the center of the circle is 3, 5, so x minus 3 squared plus y minus 5 squared is equal to the root of 10 all squared. In C, we've got a line L shown in the figure, which is a tangent to the circle C2 at the point A, and we need to show that an equation of L is given here by y is a third x plus 22 over 3. So let's go back to the figure once more. Line L is a tangent. It means that if I draw the straight line from A to T, that should be perpendicular to the line L. Remember, we've got the coordinates of point A. These were found to be 2, 8. So I could actually find the gradient of AT, find the perpendicular of this, and proceed with the fact that I know the coordinates of point A, which is a point on the line L. So we've got A has coordinates 2, 8, T has coordinates 3, 5. So we can calculate the gradient of AT by doing y2 minus y1 over x2 minus x1. This gives a gradient of negative 3, and therefore we conclude that the gradient of L must be a third. We also know that we pass through the point 2, 8, so I could use y minus y1 is mx minus x1. So we have that y minus 8 is a third of x minus 2. Remember, I'm trying to match exactly the form shown here, so I will proceed in expanding. Y minus 8 is a third x minus 2 over 3, which leads to y is a third x plus 22 over 3, which is exactly what I had to show, so as required. In part D, we are told that the region R shown shaded is bounded by C1L and the y-axis, and we need to find the exact area of R. So if I quickly go back to my shape here, my figure, I see that's the region we're trying to find, which is the region enclosed above by the curve C1 and below by the line L. So we'll be using integration to find the shaded area. So to find the area R, I'll be integrating from 0 to 2. These are the x limits, and I've got above the curve C1 with equation x cubed minus 5x squared plus 3x plus 14 minus the line which is below, which has equation a third x plus 22 over 3 with respect to x. I will start by simplifying the expression to be integrated. So that's the integral from 0 to 2 of x cubed minus 5x squared plus 8 over 3x plus 20 over 3 dx. So we are increasing the power by 1, dividing by the new power, leading to x to the 4 over 4 minus 5x cubed over 3 plus 8 over 3x squared over 2 plus 20 over 3x, and my limits are 0 and 2. If I substitute the upper limit, I get 2 to the 4 over 4 minus 5 times 2 to the 3 over 3 plus 8 over 3 times 2 squared over 2 plus 20 over 3 times 2, and the lower limit of 0 contributes 0 to the overall integral. So if I plug this on the calculator, I get an answer of 28 over 3 squared units. In question 10, we are told that a is log 3 base 2, and we need to write in its simplest form in terms of a log of 9 base 2 and log of root 3 over 16 base 2. So we will be using the rules of logarithm here. So I will start with the log 9 base 2. We notice that 9 is 3 squared, so that's log of 3 squared base 2. The power law of logarithms tells us that the 2 can come down, so it's 2 log 3 base 2, which is obviously 2a. In B, we start with the log of root 3 over 16 base 2. We know that when we've got division within the logarithm, I can express this as the difference of two logarithms. So log of root 3 base 2 minus log of 16 base 2. This is log of 3 to the half base 2 minus log of 2 to the 4 base 2. Now the half can come down. It's a half log 3 base 2 minus 4 log 2 base 2. We know that log of 2 base 2 is simply 1, so this is simply a half a minus 4. In II, we are asked to solve 3 to the x times 2 to the x plus 4 is 6, giving our answer in its simplest form in terms of a. So let me start with what we're given. It's 3 to the x times 2 to the x plus 4 is equal to 6. So I will take logs of both sides, base 2. So log of 3 to the x times 2 to the x plus 4 base 2 is equal to log of 6 base 2. I will split the product into log of 3 to the x base 2 plus log of 2 to the x plus 4 base 2 is equal to log of 3 base 2 plus log of 2 base 2. So I'm writing 6 as 3 times 2. So this leads to x log 3 base 2 plus x plus 4 brackets log of 2 base 2 is equal to log 3 base 2 is simply a, and log 2 base 2 is 1. So we also see that log 2 base 2 here is simply 1. So this leads to x times a plus x plus 4 is equal to a plus 1. So xa plus x is a minus 3. I will factor out the x brackets a plus 1 is a minus 3, which means that x is a minus 3 over a plus 1.